I'll tell you what you need to do. Just another reminder that my office hours next week will be canceled because I'll be away. So just a heads up about that. I'm still holding office hours today and on Thursday. Okay, all right?
And there'll be other office hours next week.
And there will be other office hours. So Ben and Grace will be holding theirs. All right, thanks.
Okay. I still have 1 more minute according to this clock. Welcome, everybody. I hope you all got your free donuts out there. I'd like to start with a quick review of a previous lecture. So, what do you call a program written in PyGas, which is a global address-based language, but it's based on Python, and it uses a Monte Carlo simulation to approximate pi, and it has a race condition, so that it gives you a different funny answer every time you run it. Anybody want to guess? Monty Python, yes. Okay, that's enough of a review. So move on to today's topic. I want to have 2 lectures on dense linear algebra. I'll remind you why it's worth 2 lectures, because it's one of the most common of the 7 dwarfs. It's used in lots of different applications. And it's not just matrix multiply. I will concentrate on that today since that's the building block, but next time I'll tell you about a number of other different algorithms and how they're organized in parallel, because just using the classical implementation does not work. And I'll remind you, you've seen it before, why are we going to reorganize it? It's to minimize communication. And I'll remind you of the lower bound that we're going to hit when we do it in parallel. So for your first homework assignment, it was about minimizing communication in the sequential case. Today it'll be about the parallel case. So let me just remind you why dense linear algebra is one of the important topics to do. So here's the heat plot that we've shown before, where the 13 different motifs or dwarfs that show up over and over again in different parallel applications. And here are a whole bunch of different parallel applications that people here and elsewhere have tried to parallelize. And if it's bright red, that means that this particular kernel, dense linear algebra, is used over and over again. And it's one of the most popular. So it is worth talking about. And as I said, it's not just matrix multiply. There are a lot of other things that fall in that category. They all build on top of matrix multiply, which is why we're starting first. So it certainly includes solving systems of linear equations, type A / B. It also includes non-square systems of linear equations. Those are called least squares problems. You're trying to minimize the 2 norm of the vector ax minus b. But there are a lot of different flavors of that too, which are all available. We'll only talk about one. But the most common case is overdetermined. You have more equations than unknowns, so you can't make it 0. But you may also have fewer equations than unknowns, in which case you can make ax minus b equals 0, but you have many different solutions. You have to pick one. So one way you might pick one is you might add an extra constraint to the problem. For example, you may say, I insist that the sum of the x's be 0, because there's some sort of conservation law they satisfy. So you can add that and go ahead and do the solve.
Just the weights.
Just the weights, okay. And you may have weights. Some of the equations may be more important to minimize than others. Then there's eigenvalues and eigenvectors, and the simplest case is just ax equals lambda x when it's symmetric. In that case, all the values lambdas are all real and the x's are all orthogonal. But if you're from civil or mechanical engineering, it should also be familiar when you have an eigenvalue problem with 2 matrices, say a stiffness matrix and a mass matrix, you want to do the same thing. And more generally, A and B may not be symmetric matrices, they may not even be square matrices. In that case, there's all sorts of generalizations that people use in practice. You don't just want to compute eigenvalues and eigenvectors, you might want things like invariant subspaces and so forth. Then the next generalization is a singular value decomposition. That's pretty close to the symmetric eigenvalue problem. And then, orthogonal to all those different problems, there's all these different matrix structures which have to be supported. Real and complex matrices, that's sort of a natural difference. But you may also have extra structures like symmetry in the real case, A equals A transpose, Hermitian, that's the complex generalization. Positive definiteness is yet another, all the eigenvalues are positive that make algorithms work specially. And then, even though we're talking about dense matrices, traditionally this includes matrices with a bunch of zeros in them of a special kind. It could be triangular, it could be banded, and if we put them all together and look in the standard library that we've been developing for many years, there are 27 different types altogether. So, so you want to pick the right one. And then, of course, there's different levels of detail. The simplest thing you can do is just please solve it for me, type A/B, but there are many other layers that people use too. You might want error bounds. You might want to use extra precision in order to get a slightly more accurate answer. And then there's all these different layers that are underneath it, like, please do apply certain kinds of special transformations that everything is built on top of. And so I'm not going to do all that structure. I'm going to just stick to a few layers, but there's plenty of books out there that do this kind of organization for you, and you can learn about what these look like. And these try to provide for you, if you like, a decision tree that, given the particular problem that I have, how do I choose? And in fact, let me see if this little demo works. The federal government maintains such a decision tree for you. It's called GAMS, the Guide to Available Mathematical Software, and it lets you sort of search through all this different software. It's not been updated as recently as I'd like. So you can click on the problem taxonomy, and you can say, oh, here I want to do number theory or linear algebra or something else. So if you click on linear algebra, then you can say, oh, I have eigenvalues and eigenvectors and determinants, so let me just try on systems of linear equations. And then you have all these different kinds of special structures like real non-symmetric matrices. And finally, it keeps on going and going. So all of this is available to you if you want to look. I'm not going to do all that detail, but there it is. Okay, so let me give you a little history of linear algebra software and how we've gotten to the state we are today. And the reason to talk about this old stuff is it's still all there, and it's still available as building blocks. So, well, maybe not the first one. So in the beginning was the do loop. That's sort of going back to ancient history in the 1960s. And that was enough to write the first library that was ever used. Here it was called IcePack, which was for eigenvalue problems. So people looked at that and they said, we're doing the same thing over and over again. Can we reorganize it and build some common building blocks underneath that to save ourselves some time? And that was the first version of the BLAS library, Basic Linear Algebra Subroutines. And that was a standard library of 15 operations, mostly operating on vectors. AXB is perhaps the most common one. You multiply a scalar times a vector added to another vector, dot products, all sorts of things. Why did people get together to do this in the community? This was a community effort. Well, it's because if you do this over and over again, then you want to make programming a little bit easier and make it more readable. You could hide all the details about optimizing it for a particular architecture under the covers, so you don't have to worry about all of your special vector SIMD instructions. But also to make it robust. So let's suppose we want to do something very simple. One of the routines here is compute the 2 norm of a vector, the root sum of squares. So what's wrong with simply summing the squares and taking the square root? Why is that not a reliable implementation? Well, if one of the entries of that vector is just a little bit bigger than the square root of the overflow threshold, the largest number in the machine, it's going to overflow. You'll get the wrong answer, even though the true answer is perfectly reasonable. So all the scaling, corner cases, all of that is hidden inside there for the details. Now, why was this called the BLAS 1? Because it does order n to the 1 operations and order n to the 1 data, vector operations. And that was enough to do the next version of the library from IcePack. That was when LinPack was invented. And now LinPack is, of course, has another name. It's the name of the benchmark that they use every 6 months to rank the fastest supercomputer in the world. And the name comes from this. The software does not come from the 1970s, right? This is sort of tuned for every new machine that comes out. And just to remind you, this is, as of last fall, the fastest machine in the world, ranked by how fast it can run Gaussian elimination using an algorithm I will sort of sketch in the next lecture. And it runs on a matrix of about 1,000,000 by 1,000,000. They get to tune that to run as fast as possible. And it's running at about 93 petaflops out of 125 petaflops peak. And it's doing that with a 10.5 million way parallelism. And it's getting about 6 gigaflops per watt. So that's currently the fastest machine in the world. So just to contrast, the 8th largest machine in the world, which is the one you're doing your homework on, which is Cori, is, let's see, getting 14 petaflops out of a 28 petaflop peak. So, you know, you're a factor of 10 slower, but it's still a reasonable machine to use for your homework. And I should say it's kind of fun to look online to, you know, because there's a lot of history. They've been using this benchmark for a long time. And if you go back far enough, you get to a little handheld device called a Palm Pilot, which could do 100 by 100 Gaussian elimination at a whopping 1.7 kiloflops. So all of that data is still there if you're interested. So that was BLAS 1. Now, that wasn't good enough, and because the issue became, even back then in the 70s, it was about minimizing communication, although it wasn't called that then. So let's just consider AXP, which is the most common kernel. You multiply a scalar times a vector x added to another vector y. We're doing 2n floating point operations, and we have to read 2n numbers and write n numbers. And so the computational intensity, which is the metric that we've used before, the number of flops divided by the number of words you read or write, is 2/3. That means this is going to be completely dominated by the cost of moving data, because, you know, the cost of a read or write is many, many times the cost of a flop. And so it was also too hard to, you know, optimize this on the supercomputers of the day, so the committee got together again, and they invented something called the BLAS 2 to go after the BLAS 1. And what they did was, instead of doing vector operations, they decided to move up to matrix vector operations. And they invented 25 new operations, which are still all available and highly optimized on, you know, on every platform today. The most common one is matrix vector multiply, so scalar alpha times matrix A times vector X. This is a rank 1 update, a column vector times a row vector. Solving triangular systems, 25 different versions, let's see, 25 different operations altogether, and about 18,000 lines of code, so not even, without any optimization. This is just sort of the simplest thing to do. And of course, all the companies in the world take these and have their teams of ninja programmers and make them very highly optimized for every platform. So why are these called BLAS 2? It wasn't just the second committee. They were doing order n squared operations on order n squared data. And so did this help the communication cost? A little bit, because if you look at matrix vector multiply, I'm doing 2n squared floating point operations, a multiply add for every entry of A on order n squared data, so I've risen from 2/3 to 2, which is an improvement, but it's still, you know, going to be dominated by communication. So what comes after BLAS 2? BLAS 3 was the next one. And the committee got together again and decided, okay, we really have to have the kernel of these things be matrix-matrix operations. And now there are only 9 operations, fortunately, and the most common one is matrix-matrix multiply, which is what your homework 1 was all about. But there are a lot of variations in that too. It could be matrix A times its transpose, solving many, many triangular systems, so T is a triangular matrix and B is a rectangular matrix. All of these have the nice property that they do n cubed operations on order n squared data. So now the computational intensity has gone all the way up to n cubed divided by n squared, or order n. That means we have a lot of opportunity to move a little bit of data, do a lot of work, and be flop bound and not memory bound. And so, if you look at all of the code that has been developed so far, there's 142 routines, 31,000 lines of code. Now, part of this software business is that you can't just write code and put it out there. Nobody trusts you. You have to produce test code for everything, too. So there's usually about as much test code as code itself. And so this is what's available to make sure you get the right answers. And I should say these 31,000 lines are only the completely bland, 3-nested loop, unoptimized versions. And so these are, again, taken by all the companies and optimized for each particular architecture. And so they end up in Intel MKL, all of these different libraries. So this is where it stood for many, many years. And it was a reasonable amount of work, because you could fit it all on one page in the documentation. So it wasn't a completely, intellectual overload to try to, think of what all these different operations were. So you can just look at this and say, what do I want to do? Does it fit into one of these patterns? Now, these lasted for a very long time. But it turns out the committee started meeting again just 2 years ago. And so why would we get together again to modify all these things? It was because the community decided they needed 3 more variations. The first one was something called batched BLAS, and that is motivated, not surprisingly, by machine learning. So all the companies, NVIDIA, Intel, they were all independently inventing versions of these libraries where instead of doing one matrix multiply, you would pass in a very large number of small independent matrix multiplies and say, please do them all at the same time, because that's what you do to train a neural net. And so the community said, okay, we should all agree on a common interface so that you can write portable code and move your machine learning code from one place to another. So the committee has not yet agreed on everything, but we're having regular meetings and trying to agree on what the interface should look like. The other reason the committee got together again was something called reproducibility. So if you take a bunch of floating point numbers and sum them, and you do it in a different order, you don't get the same answer. That's because floating point arithmetic makes round-off errors, and that means it's not really associative, right? You do it in a different order, you get a different answer. So most people haven't worried about that for a long time, but now, even on your laptop, you type a.out twice in a row, you get a different answer. And so just to give you an example of the motivation, a few years ago there was email on this list called NA Digest, where people ask numerical questions. And there was a developer from a finite element software company who said, does anybody have available a parallel sparse linear equation solver that's guaranteed to be reproducible when you run it more than once? I need it because I have customers who are civil engineers, and they have customers who require legally you get the same answer every time you run their code that says, will the bridge fall down or not? You can't change your mind. And so they're the lawyers, right? So it's the lawyers who get in the way. So after I saw that email, I sent email to the 100-odd Berkeley faculty on this mailing list who do high-performance computing and simulations, and I said, did you folks know that reproducibility was over? You can't expect that anymore. And the most common answer by far was, how am I going to debug if I can't reproduce an error? And so that's by far the biggest motivation for this committee to get together again. But there were lots of other interesting reasons. One person, Sanjay Govindji in civil engineering, says, I do fracture mechanics. I do all these simulations. I look for these very rare events. And when a rare event occurs, I have to go back and re-simulate it again from the beginning in order to find out what really happened. And if I can't reproduce that rare event, I can't do my science. And maybe the most interesting reason for reproducibility was another colleague who had a grant from the United Nations to detect illegal underground nuclear testing. And he said, well, what if my code says they did it and then they didn't do it? This would be a big political mess, right? So there are all sorts of reasons for wanting to do this, but I'd say debugging is the biggest one. And then the other, so the committee is trying to standardize that too, and I'd say there's class projects available in making this work. And then the other reason, again motivated by machine learning, was to do low precision. So 16-bit floating point is certainly one example, but there's all sorts of other low precision versions that people are trying to do. So the committee tried to do a similar exercise back in 1999 and produced a very large extension to the package, including sparse BLAS, all sorts of things, and it didn't take off. And that's because it just added too much, too many different things. And so the committee's going to have to be careful this time that we don't ask for vendors to implement too many things to have success. Okay, so that's a little history of the BLAS. And so after the BLAS 3 were invented, the natural thing to do is to reinvent all of linear algebra, AX equals B, least squares, eigenvalue problems, to use not your basic BLAS 1 operations, which is how we teach it all in freshman linear algebra, but to reorganize them so they can use matrix multiply in the inner loop. And so that requires rethinking how all of these different algorithms work. So when you think about Gaussian elimination, the way we teach it is you take one row of the matrix, add multiples of it to the later rows to zero out in a column, and that's naturally a BLAS 1 operation, and so that's going to run as slowly as possible. And so the question is, how do you reorganize everything to do matrix multiply in the inner loop? And we'll do Gaussian elimination in the next lecture. But let me just sort of tell you the current state of the art. So the algorithms that we were able to reorganize so that they're nearly 100% BLAS 3. There's still a little bit of non-matrix multiply. Linear system, so Gaussian elimination, least squares for sure. There are a bunch of other algorithms that are only half BLAS3, and the other half is still BLAS2, because we couldn't figure that out at the time. So that's eigenvalue problems in the SVD. And so I should say there's lots of innovation that's gone on since then in potential class projects, but that's the current state of the libraries. The other thing in LAPACK is error bounds for everything and lots of variations, for symmetric matrices and band matrices and so forth. So our last release, which was last November, was 800,000 lines of code and about 500,000 lines of testing. So again, you have to produce a lot of test code in order for people to trust this. And so hopefully we'll get another release out this coming year because we found a whole bunch of new algorithms for these that are going to be asymptotically faster than was possible before. So everything I've talked about so far is, if you like, from the sequential world. So is that library potentially parallel? Well, only if you can hide all the parallelism inside your calls to matrix multiply and so forth. So on a shared memory machine, those could be made parallel. But it doesn't work on a distributed memory machine. It will not scale up to the kind of platforms like Cori or anything else. And so another project began called ScalePack that began in 95, some years later than LAPACK, and it's specifically for distributed memory. It uses MPI, and uses rather more complex data structures that I'll talk about in the case of matrix multiply today. And since the algorithms are more complicated, only a subset of the functionality in the sequential case is available. And so it's all available there. So what is the current status of these libraries? They've basically been adopted by all the different vendors. And so whenever you type A/B, it's calling code that that Intel took and that Intel took from us and then optimized to make it work particularly well on their platforms. So one particular fun success story that we'll have a guest lecture on later in the semester was the use of ScalePack to decide the fate of the universe. Okay, so what's the astrophysics question? So you can go out at night and look up at the sky and all those stars, and there's three fates. They could just stay where they are roughly at the same distance, or they could be, because remember after the Big Bang they all started moving outward, so they could be accelerating. They could be getting farther and farther away at an accelerating rate. In that case, if you went out at night, at some point the sky would look rather empty. The other option is that there's enough gravity to take all those stars after the Big Bang, slow them down enough, and they'll start coming back together again. And then you go out and look up at the sky and say, uh-oh, we're going to have another Big Bang. So there's these three different scenarios. And so in order to make that distinction, what they did was they sent up a sensor on a balloon, and it aimed a very, very detailed camera at the entire universe and measured the amount of radiation coming from every pixel in the sky. And then it turns out that the astrophysical theory said, depending on what the signals that come back, we can predict which of those three scenarios work. So what was the bottleneck in doing that analysis? So you have a signal from every pixel in the sky, and for every pair of signals, you compute their correlation. And so that is in an n-by-n matrix where there's one row and one column for every pixel, and the entry of the matrix is the correlation. So it's a big symmetric matrix. And it turns out that the eigenvalue problem is what they needed to solve for that very large symmetric matrix, and they used ScalePack for that. And they've since gone on and done many other extensions of that analysis, but the best people can tell for now is that the universe is flat. That means it'll slow down gradually, but it won't, no more big bangs, and it won't sort of accelerate. And as I said, we'll have a guest lecture later in the semester on the current state of high-performance computing in astrophysics. So all of that is kind of old stuff. People are still innovating, and so here's sort of the current, or most recent projects. So multi-core and GPUs; those are obvious platforms people would like to optimize for. And so I will have a lecture next time where people had to do some particular special optimizations to make these things run fast on GPUs. And so there's the websites for the projects that are doing this. This is my colleague Jack Dongera at Tennessee. And there are other completely independent projects. So Elemental, which was started by Jack Paulson, is trying to also do distributed dense linear algebra, and he has a user community making contributions, and it's doing other things besides dense linear algebra. And there was a similar project at Texas which was trying to generate all this code automatically. So anyway, so that's just sort of a little history. And I should say that the goal that we're going to have today is to, all these algorithms should in principle hit lower bounds and minimize communication. So it turns out that not even for matrix multiply do all of these libraries yet minimize communication. So there's still a lot of work to do. So let's go back and just remind you before I talk about how to optimize matrix multiply, I'll just preach to the choir and say why we want to minimize communication. So my model of any platform, be it a sequential platform or a parallel platform, is that there are two costs: doing the arithmetic and moving data, either between levels of a memory hierarchy or between different processors over a network. And so the model I'm going to use in order to say whether we've hit a lower bound is I'm going to count 3 different properties of my algorithm. I'll count how much arithmetic it does, count the flops. I'll count the words moved over any one of those wires on the previous slide. And I'll count the number of messages. And a message is a bunch of words packed together into one contiguous chunk and sent all at once. And each of those are properties of the algorithm, but they all have different hardware costs. So the properties of the hardware are the time per flop, the time it's to send one word over the network, that's the reciprocal bandwidth, and sort of the latency, which is the slowdown it takes to get the message from one end of the wire to the other end of the wire. Those last 2 terms are communication. And as you've heard before, these 3 hardware parameters, time per flop, time per word, and time per message, are very, very far apart, orders of magnitude. And with hardware trends, they're growing apart exponentially. And here's some old data saying how fast they're growing apart. This data is from when Moore's law was not officially dead yet, but it still sort of applies. And so everything is getting better. But flops are getting better much faster. This used to be Moore's law, and now it's because of multi-core parallelism. The DRAM, the bandwidth is also getting better, but much slower. The latency is also improving, but much more slowly again. And so what this means is that even if your algorithm is not communication bound today, it may be next year or the year after that. So you want to minimize communication to save time. But time is not the only metric. It's also energy. And so here's a plot you may have seen before too, on the number of picojoules on a log scale it takes to perform a whole bunch of different basic operations on the computer. And this is a very old slide. So let's just say comparing 45 nanometer technology, which is like 5 years ago, with something like 11 nanometer technology. And so you can see that the time to do, the energy to do one double precision floating point operation is an order and a half, 1.5 orders of magnitude less energy than to move the data off the chip. Everything is getting better. 2018 is better than this old technology, but flops are getting better much faster. So now the difference between that bar and that bar is like 2.5 orders of magnitude more energy to move data off your chip than to do a flop. So whether you're worried about the $1 million per megawatt per year it costs to run your data center, or the battery in your cell phone dying, or how long it takes to keep your drone in the air, depends on your funding agency, then you want to minimize communication to save energy. Okay, so this is going to be our goal. And in particular, I would ideally like to minimize it along every wire in that picture, in the architecture. So minimize the traffic between the L1 cache and the L2, L2 and DRAM, DRAM and the network. And I should say there are 2 approaches that people use that are orthogonal. We like them both. One is to overlap, do the communication and the computation at the same time. That's good, but it only gives you a factor of 2 if they overlap perfectly. But if you actually come up with a new algorithm that doesn't do the communication in the first place, then you can have arbitrary kind of speedups, much, much larger than factors of 2, and we'll see those later. So now let's go do this all for matrix multiply and see how much better we can do than even homework 1. So, but I'll start by reviewing these ideas and say what did we do in the sequential case? How does it generalize to the parallel case? So what I'm going to do is I'm going to take my 2 matrices and break them up into blocks. I'm going to break them up into B by B blocks, and I will have 3 nested loops over those blocks. In the inner loop is going to do a B by B matrix multiply. And if I pick B small enough so that I can read all of these 3 matrices into cache and keep them there, then I'm just going to do 4 B squared reads and writes. they all live in cache, and then I do b cubed multiply adds, and it doesn't cost any more memory traffic. And so the whole cost of doing that is going to be n cubed divided by m to the 1/2, where m is the cache size. And that's when I pick these blocks, so all 3 blocks just fit in cache. So they're all about square root of m by square root of m blocks. So, and just again to review, I won't do this in any more detail. What if this is good enough if you have 2 levels of memory? What if you have more levels of memory? And we talked about that in an earlier lecture. You might have to have more nested loops or do a cache oblivious recursive algorithm. But that's the sequential case. I want to do the parallel case. So here is the sequential theorem, and now I'm going to state the generalization. So no matter how you do matrix multiply, the one in the previous slide is one example, but any organization of matrix multiply has to move at least n cubed divided by the square root of the cache size words between slow memory and fast memory. What's the comparable result for the parallel case? It's almost exactly the same theorem, you just have to interpret it a little bit differently. So the question is, what is m in the denominator? So m is, what does memory size mean in a parallel case? That's going to be the memory on each processor. So what I'm going to ask is how much data has to move in and out of one processor. That's the communication cost over the network. So m is going to be the memory per processor, and I'm going to assume that it's load balanced. Everybody's going to own one piece of the data if I have p processors. And so what's the numerator? It's the number of flops that processor is assigned, and every processor, if it's load balanced, will get one piece of the work. So the numerator becomes n cubed over p. So that's the numerator. The denominator is one piece of all the data. So let me plug in n squared over p roughly there. And so my lower bound turns into n squared over the square root of p. And so that's going to be my initial goal for matrix multiply and the rest of linear algebra. I want to organize it matrix multiply, so this is how little data I can move. And there's some classical algorithms that have been known for a while to do that I'll talk about. Okay, so this is just repeating what I said before. So if m is the size per processor, then the number of words moved is going to be the flops, say n cubed over p, divided by the square root of the cache size, which is perhaps n squared over p. And as I said, that was known for matrix multiply, but now we know it holds for just about anything that smells like 3 nested loops. So you can just use your intuition for smells like 3 nested loops, but it basically covers all of linear algebra. It covers all the basic linear algebra subroutines. They have the same lower bound. LU, that's Gaussian elimination, same lower bound. QR, eigenvalue problems, SVD. Tensor contractions. So what's a tensor? A tensor is not a 2-dimensional matrix. It could be 3 or 4 or whatever. And a contraction is basically a matrix multiply generalized to more dimensions. That's certainly not 3 nested loops, but the same lower bound. Flops divided by the square root of the memory size. It applies not just to one subroutine call, if you like. It can apply to whole programs, no matter how. So if you're doing a lot of matrix multiplies, this says that no matter how you organize it, no matter how you interleave all of those matrix multiplies, you can't do better than this lower bound, which is doing one at a time. So for example, if you wanted to compute a power of a matrix, k matrix multiplies, this is the same lower bound. It applies not just to dense linear algebra, it applies to sparse linear algebra. And in that case, the number of flops is not n cubed anymore. It's however many flops you happen to be doing for your sparse matrix, which depends on its structure. And so this is a very general result. It applies, as we have already seen, to both sequential and parallel algorithms. And you don't actually have to be doing linear algebra. You don't have to be doing multiply adds in the inner loop. You could be doing anything. So for example, if you're doing maxes and pluses, that turns into a famous graph theory algorithm called Floyd-Warshall, which finds all pairs shortest paths, and the same lower bound applies, and it gives you optimal ways to do that particular graph theory algorithm. And so this is a very general result. And now you may say, well, what about other ways to do matrix multiply, like Strawson and so forth? Well, we have generalizations for that, and I'll sketch those later. So all of this extends. And so that was the lower bound on the number of words moved. But my other metric, remember, is how many messages, what's the latency cost. So here's going to be my very simple goal for how many messages I send. Suppose I want to send a bunch of words. How do I minimize the number of messages? Well, I'll simply pack them all into as large a message as possible, and that'll minimize the number of messages. what's the maximum size of a message? The whole memory, right? So that's sort of and I can send it most M words at a time. So that says the number of messages is at least, a factor of M smaller than that. So I can't do any better than a factor of M smaller than that. And we'll actually hit that lower bound for a number of algorithms. Okay, so let me just plug in what this all means for dense linear algebra on a parallel case. So it's load balanced, so what's the number of flops is going to be n cubed divided by p. That's what's going in the numerator. The denominator is going to be the size of the local memory in each processor. And the simplest case that we'll start with is that we're going to use as little memory as possible, and everybody gets one piece of the data. So all of it, it's all load balanced. So if I have n by n matrices, the total memory is n squared, everybody gets one piece of it. So I'm going to plug that into the denominator. And so there's a little bit of algebra, and the number of words moved, our goal is going to be n squared over the square root of the number of processors. And the number of messages is going to grow with the number of processors. It's going to be proportional to the square root of p. And so what that tells us is that depending on the relative cost of latency and bandwidth, I may want to use more processors or fewer processors because this cost goes up and that cost goes down. So that's a tuning parameter for your particular hardware. And I'm pleased to say all this work won a Best Paper Prize a few years ago to sort of write it all down. So what about the libraries that I was telling you that are the standard ones that are on all these different platforms in LAPACK and ScalaPACK? Mostly not yet. So in fact, not even for matrix multiply in parallel do they hit the lower bound. So there's still lots of work to do. And there are lots of other algorithms that we know about, but we haven't actually gotten into the software yet. So you can think of those as class projects. So what are the goals? We want to minimize the number of words moved, minimize the number of messages. That means we need new data structures. It turns out the obvious way of representing matrices as square arrays doesn't minimize the number of messages. So we have to deal with that. We'd like to minimize for all the different levels of memory hierarchy. Cache-oblivious algorithms would be fastest there, but they don't minimize the number of flops. Sometimes they do extra work in order to be cache-oblivious. And so this is all dense linear algebra. What about sparse linear algebra? Because I did say that the lower bound's held there. It turns out that you need to have some assumptions about the structure. So for example, suppose you want to multiply two diagonal matrices. There's no magic. The obvious algorithm that just does, touches everything once is the best you can do. So you need some structure in order to hit the lower bound. And it turns out that if you're doing a finite element model in 2D or 3D, that has the right kind of structure, and you can hit the lower bound there. And there's some matrix multiplies that come up in machine learning and MRI analysis where you're multiplying a dense matrix times a sparse matrix. And again, you can hit the lower bounds there and get very large speedups. Okay, so that's sort of the history and motivation. And so now I want to go and just dive into matrix multiply and how do we make that go as fast as possible. But are there any questions about that overview before I start doing matrix multiply? Okay. So the first thing I have to do is figure out which processor is going to own which part of the data. And so let me just give you some natural choices and tell you that unfortunately the simplest one doesn't work. So the natural thing, suppose I had 4 processors, would be to give each processor 1/4 of the data and 1/4 of the columns. That's the first one there. That's called a column block layout. Now, it turns out that we will prove later that you can't hit the lower bound for matrix multiply with that particular layout. But there's another reason it's not very good. And let me just use your intuition about how Gaussian elimination works. What does Gaussian elimination do? It starts, up here, and it works its way down the diagonal, and it keeps processing, a smaller and smaller, lower right corner of the matrix. So let's suppose I've finished processing down to here, and I'm just working on that submatrix in Gaussian elimination. Processor 0 is idle. It has no more work to do. And so this is not a good use of hardware resources for Gaussian elimination, as we'll see. So here's a natural way to try to fix it. Let me deal out the columns like a deck of cards. So every processor gets, in this case, every 4th column. So now, every submatrix that I pick down here is load balanced. Every processor still owns roughly a quarter of all the data, so that should fix that problem. But now, remember, what do I want to do locally on each processor? I'm probably going to want to do matrix-matrix multiplies, because that's what I want to call the BLAS 3 locally. And here, they're all single columns, so that's not going to work. So let me compromise between those two, and let me try this particular layout. So now I'm still going to deal out blocks of columns like decks of cards, except instead of dealing out one column at a time, I'll deal out B columns at a time. That'll let me do B by B local matrix multiplies, which will hopefully be fast enough. But now I have a different bottleneck, because in Gaussian elimination, I'm only going to have one processor owning that whole block of columns, and the work that processor has to do is going to be the bottleneck. And all of those comments apply to transpose versions, where I'm doing it by rows. So I'm really going to have to shift to a two-dimensional version. And so here's the simplest two-dimensional layout, and this has the same load balancing problem. By the time I get halfway through the work, there's only one processor busy. So there's the answer. It's that 2D block cyclic layout down here. I'm going to divide up my matrix into B by B blocks, where B is big enough that a local matrix multiply runs fast. And I will take a little pattern, in this case 0, 1, 2, 3 are the processors that own it, and just repeat that everywhere. So now, no matter which submatrix I take, like that one here, it's still load balanced. Every processor owns about a quarter of it. I have parallelism down a column, so which is what Gaussian elimination needs. And when I do the local work, I can do B by B local matrix multiplies. So that's the data layout that we will eventually use to hit all of our lower bounds. It's not necessarily user-friendly, but that's what you need to do. So in fact, one of the projects we've had in the back of our minds for a while is that if the user hands us this kind of layout, why don't we automatically decide, using some machine learning, what's the optimal layout to switch it to, and whether it's worth the conversion cost of copying the data from here to there, running your algorithm there, and then copying it back, right? So that's work to be done. Okay, but let me now just do some simple stuff on the simple layouts before I get to the complicated one. And let me just do matrix vector multiply and sort of do some simple performance analysis so we can see what's going on. So I want to do A times X, where A is a dense matrix. And I'm going to keep it very simple. I'm going to use a row block layout with 4 processors. So each processor is going to own 1/4 of the rows. And A sub I is going to refer to the N over P by N submatrix of A. And so in each processor will also own 1/4 of the entries of Y and 1/4 of the entries of X. So because that's going to be my starting point. So what is the algorithm going to look like? I need to multiply, in order to compute those entries of Y, I need to multiply that submatrix of A times this entire vector of X. But I don't own that. I only own that quarter of it. So what I need to do is every processor has to broadcast its submatrix of X to all the other processors. Then everybody has a redundant copy of the vector X. And then everybody can independently do a short, fat matrix vector multiply to get the local data. Okay? And so that's the perfectly natural algorithm to do. And so here is so this part you have to do anyway. The extra cost of communication is broadcasting. Every X sub I has to go to everybody else. So we'll take that into account. So what if I chose, instead of doing a row block layout, to do a column block layout? It would be almost the same algorithm, except now I don't have to broadcast X anymore, because I only have to multiply a tall, skinny matrix times the local copy of X that I need. But when I do that, I get a contribution to Y that I have to combine with everybody else. Everybody is going to contribute a partial sum to the entries of Y. So that means I have to do a reduction sideways. Everybody has to contribute to the final answer. So I get communication that way. And finally, the algorithm we may want to use is this 2D layout, which I've shown here. If I have 16 processors, everybody owns a square submatrix. And so what happens here, I need to make sure that if processor 0 owns P0, processor 1 owns that block of P1, I have to broadcast this entry of X so that everybody in that processor column owns those entries of X. Everybody in this processor column owns those entries of X. Then everybody does a local little square matrix vector multiply, and then I have to do a sideways reduction. So all of these guys have partial sums that have to be summed into that. So I have a smaller broadcast, all happening in parallel. So I have broadcasts, in each column, and then I have reductions in each row.
The reductions into where?
The reductions go into the answer, y. Y equals a times x. So this guy is going to have a ax, if you like, a1x1 plus a2x2 plus a3x3. All of those are going to be contributions to those first entries of y.
Okay, so y ends up being stored not where x was stored initially.
Right. Y does not overwrite x. Right. So y and x are, so that's the operation. They're separate arrays. Yeah, it's easier to do it that way. It doesn't take that much extra memory. Okay, so that's sort of a little warm-up to see what is required to do a matrix vector multiply. So let's move on to matrix multiply of square matrices. And I'm going to just talk about the classical algorithm. I'm going to do 2n cubed multiplies and adds. And so what are my choices that I have to make? What is the data layout going to be? I could have a 1D layout, or I could have a 2D layout, and there are even other possibilities. It also is going to depend on the hardware that's underneath and how the different processors can communicate with one another. So the simplest thing to think about, we'll start with this, is just a ring. So everybody, all the processors can only talk to their left and right neighbors, perhaps. That's a very simple thing to build, but it will not let us hit the lower bound. A more common kind of connection is when everybody's connected in a torus. So a two-dimensional torus means you're connected to your left and right and up and down neighbors in a two-dimensional grid, and then connecting around on the sides. People are also building three-dimensional toruses. I think IBM has built five-dimensional toruses. So that's different kinds of things. There's all sorts of innovation going on in how connections work. And then, given these decisions, we have to figure out how do we schedule the communication from one processor to another. So just to remind you, here's going to be my model. The time to send a message is going to be the latency plus the size of the message times the reciprocal bandwidth. And the way I'm going to sort of summarize whether an algorithm works well or not is I'm going to measure its efficiency as follows. I'm going to take the serial time, which is just going to be 2n cubed, and I'm going to divide it by p times the parallel time. So the parallel time, the best possible thing, if I had perfect speed up, the parallel time would be 1/p of the serial time, so this would be 1. And the question is, how close to 1 do I get? It's going to depend on how clever my algorithm is, and p and n and all these different parameters. So I'll see how close I get. But let's start with the ones that don't work very well, which is a 1D layout, won't be able to hit the lower bound, and a ring topology, just to see what happens. So let's suppose that I have 8 processors, and each processor owns 1/8 of the columns of the matrix here. And so just to write down the so this is just one matrix. All 3 matrices are going to be stored the same way. And I'm going to, for notation, I'm going to let A sub I be this particular n by n over p submatrix. And similarly, BI and CI, just to write down the math. And I'm also going to have to refer to submatrices. So I'm going to let that square up here be B sub 1, 1, the square right below it be B sub 2, 1, and so forth. So this subscript is going to refer to an n over p by n over p block. And what is the algorithm going to do? Well, so what does it take to compute the ith block column of C? Let's say the first one, so C0. C0 is going to be the whole matrix A times the corresponding block column of B. That's what linear algebra does. And so, remember, I can only access A by columns, so that means I have to take the jth column of A and multiply it by a block of B. So that's the math that I need to communicate, make sure everybody's in the same place at the same time. So there's the formula again. And let me try 2 very simple pieces of hardware underneath it. The first one is going to be just everybody's talking over the internet, over an Ethernet. So that's like a bus. And that means only 2 processors can communicate at once. So since it's one shared wire, if you like, there's only one communication possible at a time. So that's a very primitive thing, but let's do it anyway, just as a warm-up. And then we'll consider that ring topology where everybody can talk with their nearest neighbors at the same time. So everybody's connected to their left and right neighbors. So here is the algorithm for matrix multiply for the 1D layout. Everybody owns a block column, and it's on a bus without any broadcast. So only two processors can talk at the same time. And so what's the algorithm? So what can I do without any communication at all? I can take the block column of C that I own. So my proc is my particular processor number. Every processor is running this identical code. It's just that everybody has a different value of my proc. So I take my block column of A, my block column of B, and multiply by the appropriate block, I take my block column of A and multiply it by the appropriate block column of B to update C. So that requires no communication. But now, what do I need to do? I need to get every other block column of A locally to update C. And so that means I'm going to loop over all pairs of processors. And if I'm the right processor that's being asked to send it, then I send my block column of A to processor J. And if I'm processor J, I receive it and do the local matrix multiply. So this loop is very slow, right? I'm looping over all pairs of processors because only one pair can talk at a time. So what's the cost of the inner loop? Then we'll do the rest of the calculation in the next slide. So this matrix multiply, I'm doing an n by n over p by an n over p matrix multiply. There it is. And the communication is sending one block column. So that's one n by n over p matrix. So that's the number of words I'm sending. There's the bandwidth cost, and it's one message, so it's one alpha. And so I've just repeated that up there. And since I can only have one pair of processors active at a time, how many times do I execute the inner loop? It's basically p squared times. So this is basically a sequential algorithm. You might ask, why would I ever want to run this? I'll tell you in a second. So here's the running time. It's p squared times the cost of the computation cost of the inner loop, p squared times the communication cost. So the total time is the sequential flop time, 2n cubed, p squared messages, and p times n squared b. So this is worse than a serial algorithm, right? So the serial algorithm would just be this first term. All of this is much, much worse. So why would you ever even be motivated to do something like this? I mean, you should buy a new computer if this is your only choice, but suppose that your data didn't fit on one computer, right? And you had no choice but to have it spread out over multiple computers on this terrible bus network. This would be your only choice. But let's go on to the better algorithm. So now, still the same layout. Everybody owns an n by n over p block of A, B, and C. But now everybody can talk to their neighbors on a ring. And so what is my algorithm going to look like now? I'm going to basically take my copy of my data and send it to my neighbor. Everybody's going to do that at the same time. So I'm going to copy my block column of A into a temporary array. I'll do my local matrix multiply that I can do. And then I only have to do this p minus 1 times. I'll send the copy of my data to my neighbor to the right. I'll simultaneously get my neighbor to the left who's going to send me data. And then I will do my local matrix multiply. And after p steps, my submatrix will have visited every other processor, and it will all be done. So you've already seen this algorithm. It's the same as gravity, right? I have to get all possible pairs of block columns of A and block columns of B have to be in the same place at the same time. And so it's basically the same idea as homework 2. And there's various optimizations you can do, but let's again say what the complexity is going to be. So the inner loop is going to be a matrix multiply, so same cost for the floating point. And let's say that this is 2 messages. So I'll have 2, and there's one message coming from my left, one message to my right, and each message is going to have one latency cost, and it's going to be sending one n by n over p matrix. So that's the cost of the inner loop, which I'm just repeating right here. And how many times do I execute the inner loop? P times. So I just take this thing and multiply it by p, and here is the formula. So let's see if we like this formula. So the first term is 2n cubed over p. That's the flop time. That's perfect. I have a perfect p-way parallelism for that. Can't do better than that. But the number of messages is growing like p, and the number of words sent is growing like n squared. So I claim that as long as I have this kind of network, I can't do any better than this. And that's because A has to move to every other processor. I'm basically doing gravity. Every pair of processors has to, every pair of block columns has to be in the same place at the same time. And so I can't do any better than this if I have this 1D layout on a ring. But, well, okay, so let's ask, what's my parallel efficiency? Do I get good speed up as I let the problem size grow? So remember, the parallel efficiency is going to be the sequential runtime. That's just 2n cubed. And then the denominator is p times the parallel runtime. So I multiply this quantity times p, and all the n's cancel, a lot of the n's cancel. And what do I get? I get this term, which is latency. This term is bigger, so I'm just going to ignore that term, and I get 1 over 1 plus this term, which is p over n. So as long as n is my matrix dimension is much, much larger than p, this is going to get small, and my efficiency will be good. So this is not a terrible algorithm. If n is much, much larger than p, I will have pretty good parallel efficiency. But what would the lower bound be? How far am I from the lower bound? What did I claim that I could get this cost down to? Remember, it was the square root of p messages, not p messages. So I'm off by a factor of the square root of p, and that's pretty big. And what was my goal for the bandwidth cost? It was n squared over the square root of p. So I'm off by a factor of the square root of p there too. So I still have a ways to go. Okay, so back to this 2D layout. We're now going to go down here and figure out how to make it work for that, because that's the layout that we need to hit the lower bound. And here's a little history of the algorithms. The first one, which is what's in Scala-Pack and has been reinvented many times, it's called SUMMA, Scalable Universal Matrix Multiply Algorithm. Some person made up that name a long time ago. And this attains the lower bounds to within a factor of log p, which is close enough for a lot of purposes. Now, historically, the first algorithm that did this was in a 1969 PhD thesis. But it made a bunch of assumptions. It actually hits the lower bounds perfectly, no log p's, but it made some assumptions that a and b were square, which isn't always true, and that the number of processors was a perfect square. So I'll just mention that, but I'll just tell you about SUMMA. Recently, we found a new algorithm that's even faster, and I will tell you what that is. We're calling it 2.5-dimensional SUMMA, and it uses more memory to communicate even less than the lower bound. And so this is surprising that it turns out that you don't have to use the minimum amount of memory. If you have extra memory, you can go faster. And then I'll say a little bit about parallel Strawson at the end, because that also can be parallelized quite effectively. So let me present SUMMA. And this is what's built into Scala-Pack in the parallel BLAs. So if you're wondering, the BLAs, if you put a P in front, there's the parallel versions, and they're all on the same website. So let me go explain how that works. So the way that SUMMA is going to work, it's going to organize the usual 3 nested loops as a bunch of what I'll call outer products. So I'm going to loop over all of the kth columns of A and kth rows of B. And when I multiply the kth column of A and the kth row of B, I get an n by n matrix. And I'm going to sum all those up, and that's just one particular way of expressing that. So in fact, the way SUMMA is going to work is it's not going to multiply one column times one column. It's going to multiply a block of one column times one row. It's going to multiply a bunch of columns times a bunch of rows. And so here, just to illustrate, if I chose 4, that's going to be a tuning parameter. I'll take 4 columns of A, multiplied by 4 rows of B, and move on and on. Okay, so that's going to be the math. And so here's the picture of the algorithm. So suppose I have 16 processors, more generally P processors. I'm going to arrange them in a square root of P by square root of P, in this case 4 by 4 grid. And so this represents both the grid of processors and which processor owns which submatrix. So that particular processor owns that n over 4 by that n over 4 submatrix of A and B and C. So that's going to be my data layout. And what is the algorithm going to do? It's going to take at every step, it's going to take a block of columns of A, a block of rows of B, and multiply them together and update the whole matrix. So that's going to be, so the inner loop is going to be red times blue and adding that to the whole matrix. How am I going to get that to work? So because who needs to own, so let's look at this processor here. What data does that processor need in order to update that particular block of C? It needs that subblock of A, it needs that subblock of B, which it doesn't own, and then it can do the local work. And so the communication at every step is that every processor who owns a subblock of A is going to broadcast it sideways so that everybody in that row of 4 processors owns it. Everybody who owns a subblock of B is going to broadcast it down, so every one of these 4 processors in that column will get a copy of that. And when each processor gets its copy of that subblock, and that subblock can then do the matrix multiply. Okay, and then this is just going to march, this red one will march sideways and that blue one will march down. So that's intuitively what the algorithm is doing. Let me write down the code, and then I can do the counting. So I'm going to loop over all blocks. How many and so I have to choose how many columns are in that block, how many rows. I'll call it B. B will be a parameter that I choose. So I'm going to have loop, n over B outer iterations. And then for each processor row, and this is a square root of P by square root of P block. So I'm going to have, for everybody in this block row, I'm going to take the submatrix that I own and broadcast it sideways. So this is going to be a broadcast, and it's going to use a binary tree, the usual way we do broadcasts. Then everybody who owns this block will take their submatrix and broadcast it down, again using a binary tree. And then I receive, and I do a multiply. So this is just the code for what I said in the previous slide. So now let me annotate it and just do the counting. So this is, it's the same code as in the previous slide. So how much does this cost? I'm broadcasting this submatrix. How big is the submatrix? It has n over square root of P rows, B columns, so that's the size. And it's a tree, so I'm doing it log square root of P times. And the number of messages is the number of layers in the binary tree. That's the log of the square root of P. That's broadcasting A. Broadcasting B is the same thing. And then here I'm doing a matrix multiply of an n over square root of P by B by B by n over square root of P, multiply all those dimensions together, and that's the number of flops in the inner loop. So, and then how many times does all this happen? Multiplied by the number of outer loop iterations, which is n over B, and the total words moved is n squared over root P times log P. That's almost the lower bound. The lower bound that we had before was n squared over root P, so we're almost there. And in this world, if you're within a factor of log P, you usually declare victory. Now, in fact, you can get rid of that log P factor by being more clever, but it would make the algorithm harder to read. So let's just leave it at that. It's possible to get rid of log P. How many messages do I have? It's log P times n over B, because log P times n over B. Log square root of P, same thing. And so how do I choose B? Remember, B is my tuning parameter. How big? So the bigger the B, the better. How big can I make B? What's the upper bound? If I wanted to, I could make this as wide as the entire set of data that I own. That would be n divided by the square root of P. And if I plug that in, then I actually get my lower bound, which is square root of P. So there's a tuning parameter. So why wouldn't I just always pick B to be the maximum, which would be n over the square root of P? It would double the memory, right? I would need to have all this extra buffer space in order to do that. And maybe I can, maybe I can't, but that's a tuning parameter. So this tells me that I can get very close to hitting the lower bound. So let me show you some very, very old performance data before I show you some much newer performance data. So this is the performance of matrix multiply on some very old machines for various values of n and various numbers of processors, so 4, 16, and 64. And the question is, how do I measure the performance? And so the easiest thing to do is to look at this table here, and I'm going to show you the speed of parallel matrix multiply divided by P times the speed of sequential matrix multiply, because I can't possibly go faster than P times faster than local dgem. So ideally, all these ratios would be equal to 1. And but they aren't. They're a little bit less because there's communication overhead. Let's just look at them and see how they scale. So first of all, they're all half or bigger. So we're getting half of P, which is nothing to complain about. The other thing is that if I fix the number of processors and let n grow, all of these ratios, efficiencies get higher, closer to 1. That's because as n gets bigger, the flops start to dominate the communication, and I'm getting closer and closer to perfect speed up. So I expect these numbers to grow larger from left to right. What happens if I fix the problem size and increase the number of processors, parallelism? All these ratios go down, and that's because the flops are staying the same, but communication is becoming more and more dominant, so I get, this is sort of scaling in the way that you'd sort of expect it to scale. And depending on your problem size and your matrix size and the number of processors, it may not be worth using too many processors. But we'll come back to that. So I claim that we can actually do better than all of these algorithms. And why is that? What we noticed was that we had this implicit assumption that we used as little memory as possible, right? That we had exactly one copy of the data. What else would you do? But it turns out that all of our lower bounds, which have an m in the denominator, are still true if you make m bigger. So potentially you can communicate less if you use more memory. So the question is, why would you want to use more memory? It turns out that if you replicate the data, make extra copies of your A and B matrices, you can actually communicate less and still hit the lower bound. And so let me tell you what the lower bound is, this new lower bound, and then what the new algorithm is. So let's suppose that instead of just one copy of the data, I can fit C copies of the data. And C is a parameter depending on your hardware. And so I'm just going to plug, so instead of m equals n squared over p in the denominator, I'll just plug in a factor of C, and I can tell that the number of words moved is going to go down by a factor of, that square root turns into a square root of the number of copies. So I can reduce the bandwidth cost that way. And that 3/2 turns into the number of copies of the data to the 3/2. So for example, suppose I had enough memory to have 4 copies of the data. I could cut the communication cost in half and the latency cost by a factor of 8. And we can actually get very large speedups by doing that. In fact, this algorithm, one special case of it, has been rediscovered many times in history. This is not unusual. The special case is when you have exactly p to the 1/3 copies of your data. And this was called three-dimensional matrix multiply in the literature. Why is that? Because what you do is instead of taking your p processors and laying them out in a square grid, square root of p by square root of p, you lay them out in a cube, cube root of p by cube root of p by cube root of p. And everybody in every layer in that cube gets a copy of all your matrices. That's why you have p to the 1/3 copies. And so the trouble is that if you have 1,000 processors, you may not have 10 times the memory. What we would like is an algorithm that uses whatever memory you have available, and you can tune it for that. So here's the algorithm that does that. We're calling it 2.5-dimensional matrix multiply, because it kind of interpolates between the 2D summa algorithm and the 3D algorithm, which assumes you have lots and lots of memory. And so here's the idea. Let's suppose I have exactly enough memory to fit C copies of the data. I'm going to take my processors and lay them out in this kind of 2.5-dimensional grid. They're going to be C layers. Each layer will get a redundant copy of the data. And each layer will have P over C processors laid out in a square. So root P over C by root P over C. So if I had 32 processors in memory for 2 copies, that's what it would look like. So what's the algorithm? Initially, let me just use these 3 indices to indicate which processor is which. So initially, I'm just going to have all my data sitting at the top. So there's going to be one copy of A and B, sitting up here. So this processor at the top will own an n over 4 by n over 4 submatrix of A and B. The first thing I do is a broadcast. Every processor broadcasts down, so every one of those C layers gets a copy. That's the first step. The next step is independently, every layer runs 1/2 of summa, or 1/7 of the sum algorithm. It's only going to compute 1/7 of all those partial sums that the algorithm would normally have computed. When I'm done with that step, which is the dominant step, I have all these partial sums stacked on top of one another, and all I need to do is a reduction in the vertical direction, collect all the partial sums, and the true answer appears on the top. I won't do all the subscripts, but that's the basic idea. So the question is, how much does this pay off? And we've gotten very large speedups by doing this. So here is some more recent and simple performance data. So in this case, this is strong scaling. So this was on an IBM BGP. It was a fixed matrix of size 65,000 by 65,000. The horizontal axis is the number of processors from 256 up to 2K, and the vertical axis is percent of machine peaks, so up is good. The best we could hope for is 100%. Here is the new algorithm, the 2.5D matrix multiply, and you can see that's a horizontal line. It scales perfectly. So if I double the number of processors, it runs exactly twice as fast. Whereas if I use the algorithm which has one copy of the data, it's trailing off. It's getting slower because the communication is more expensive. So let me do a little more careful breakdown of this time. There's a speed up of a factor of 12 by doing this. So this is, again, this is on 16,000 processors. For a small matrix, 8K by 8K, and a much larger matrix, 131K by 131K. And the vertical axis is, again, percent of machine peak. The blue, and so up is good. The blue is the classical algorithm with one copy of the data. It's running at about 5% of machine peak. Whereas if I use 16 copies, that turned out to be the right number, then I can go at 25% of machine peak, or roughly 12 times faster. Now, for a larger matrix, it was dominant here. The flops are much more important, so there was only a factor of 2.7x speed up. So let me do a little timing breakdown. This is sort of a performance analysis that you might want to do for your class project too, if you do that. So let's take the time and break it down into the time spent doing computation, so local BLAs, the time spent communicating, actual MPI calls, and the time spent just sitting around idly waiting for stuff to arrive. So you can see that here's the communication time, and it dropped by this 95%. All the idle time went away too. That's because this was very carefully implemented on a three-dimensional torus, so that you kept all the wires busy all the time, and there were no traffic jams on the network. That was important. And also, the flops went faster. So the green bar is the flops. So how could that possibly go faster? We're doing the same 2n cubed over p flops. And the answer was the local matrices were larger. So the BLAS3 ran faster because of the replication. And so that meant there was faster local performance because of the local memory hierarchy. And so that overall was a factor of 12. Now when we went to a large matrix, then the computation was about a third, and it was already running at the peak speed of the local BLAS3, and so we still got rid of like 95% of the communication, but it only went 2.7 times faster. So I'm pleased to say this won another Best Paper prize. So a few years ago, I was teaching this algorithm in this class, and there was a student who was a grad student in neuroscience, and he thought it was a good idea. So after he graduated, he did a startup, and it was acquired by Intel last year. So it was Nirvana, a deep learning startup. So anyway, who knows what other good ideas you'll have here. So let me tell you that now that this picture here, where I have this horizontal line, I call that perfect strong scaling. Let me actually convince you this really does scale perfectly in both time and energy. So every time you add a processor, you don't just have a processor, you have memory, right? It comes with that. You're paying for that extra hardware resource, so you should use it, and as part of your algorithm. So let's just do a little algebra to see how things scale if every time you add a processor, you use its memory as well. So let's start with the minimum number of processors that you need just to fit all the data. So P processors, each one has memory of size M, and that just barely fits my 3 n by n matrices. And I'm going to increase the number of processors by a factor of C, which is going to increase the total memory by a factor of C. Let's see what happens if I use all that memory. So I'm going to write down the algebra just to see how it scales. So I'm going to have 3 terms: the seconds per flop, the seconds per word moved, and the seconds per message. We've had that model before. And I can write down this messy formula, which is the sum of all those 3 terms, when I run it with C times the number of processors. But all I care about is how it scales. And it scales perfectly. If I increase the number of processors by a factor of C, the flop time goes down by a factor of C, the bandwidth goes down by a factor of C, and the latency goes down by a factor of C. So that's what I mean by perfect strong scaling in time. So let's talk about energy. I need a simple model for energy. And so it's perfectly natural. So E, subscript meaning energy, I can count the joules for all those basic operations: joules per flop, joules per word move, joules per message. But of course, a computer burns energy in lots of other places too. So just keeping the memory turned on burns a lot of energy. So let me add a term for that. the joules per word of memory used per second, just to keep the memory turned on. So that's going to, I have to multiply that by the memory size. And then, there's the leakage and the uncore and the wires and all of and the fans. Let's just add all that together and another joules per second term. Put that all in there. So again, I can write down another long, messy formula, which is the energy to do my n by n matrix multiply using C times P processors. All I care is how it scales, and it scales perfectly. It takes no more energy to go P times go C times faster than it does on P processors. So how can that be? So this is why this is true. I haven't changed the physics. All the processors are burning power at the same rate. I have C times as many of them, and they all run exactly 1/6 as long. And so the C's cancel, and the total energy is constant. And so I'm calling that perfect strong scaling in energy. And you say, is this sort of magic? Can I keep doing this forever? No, there's a limit. There's a mathematical limit on how big C can go. And the answer is P to the 1/3. That algorithm was rediscovered many times. The 3D algorithm is the hard limit. None of this scaling goes past that. And one sort of intuition for that is if you look at the lower bound of the number of messages, when C gets up to P to the 1/3, the number of messages hits 1, right? So there's something in the math has to change when the lower bound hits 1. And this perfect strong scaling isn't just for matrix multiply, it works for Strawson, direct n-body, and all sorts of other things too. And there's some papers on this. Okay, so let me just summarize this so I can compare it all to Strawson. So I'm just going to have a 2-slide summary of Strawson. So here is classical matrix multiply. It does n cubed flops, n cubed over p in the parallel case. Here's the complexity term that I had before, and to make it easier to compare to Strawson, I'm just going to do a little algebra, so I have a 3 up there. And because Strawson is going to change that 3, right? So it's going to be log base 2 of 7. So this is going to make the algebra simple. So that's the lower bound on words. There's the lower bound on messages. Again, I've just put that 3 up there. And we know that I can't do this forever. I can only increase it up to a factor of P to the 1/3. And then I hit this lower bound, which is the words can get that small. So what about Strawson? Remember, Strawson doesn't do n cubed flops in the sequential case. It does n to the log base 2 of 7, about n to the 2.81. So in parallel, all you do is you change the 3 to 2.81. What about the communication lower bound of the number of words? Again, just change 3 to 2.81. Now, the proof is much harder than the typesetting, but I'm just doing it this way to make it easy to do the comparison. So you can see that Strawson is also doing asymptotically less communication. Same story here. The number of messages, again, it goes from 3 down to 2.81. And what about the limit? It's not P to the 1/3 anymore. It turns out to be this magic thing. And I should say this is all true not just for Strawson, 2.81. It's true for every algorithm that anybody's ever invented for fast matrix multiply. And people keep inventing them. The current world record is something like 2.3 that was discovered back in 2014. So all of these, whenever somebody invents a new algorithm, this basically applies. And so why do we hit this lower, and there's the lower bound of the number of messages. And so why do we hit the lower bound then? It's because the number of messages hits 1, or probably log p. So that's sort of why we always hit this bottom here. So let me just show you some speed up numbers, because this is all just theory. And so here is a performance plot, strong scaling. The horizontal axis is the number of processors, from p equals 49, conveniently 7 squared, makes Strawson easier to implement, up to many thousands of processors. This is a fixed problem size of 94,000 by 94,000. And the vertical axis is the effective gigaflops. So this is, if you like, the 2n cubed divided by the time. So this is why I can fairly compare Strawson, which does fewer flops, to the n cubed algorithm. So the vertical axis is just basically reciprocal of time. So there is the classical n cubed summa algorithm, and it's down here at 20 gigaflops per node, and it stays pretty flat. So this is one copy of the data, the n cubed algorithm. Here our previous, this other green line is our 2.5D one, and it is getting closer to the peak speed of the machine. So this horizontal line is the absolute peak for an n-cubed algorithm if communication were free. We can't go faster than that. And this is the 2.5D algorithm I told you about. These blue lines are previous attempts in the literature to make Strawson parallel. And then finally, here's ours, this red line up here, which is running faster than the peak speed of the machine, because of course it's, you know, the way we're scaling it, we're pretending it's doing n-cubed flops when it's doing fewer. And this line is fairly horizontal for a long time. So it's doing, you know, a reasonable job of perfect strong scaling. Okay, so where does this fit in all the software for the rest of linear algebra? So that's the end of matrix multiply. And so the rest of the hierarchy that I'm going to tell you about next time, you know, because eventually, you know, you care about this library, which solves linear equations and least squares problems. It's built on a stack of other stuff. So at the very bottom of the stack are the BLAs, you know, your matrix multiply in your local processor. And on top of that is, you know, libraries like LAPACK. That all runs locally on one node. Then you have MPI sitting there. There's another layer called the basic linear algebra communication subroutines, which send submatrices around and do all that complicated stuff with 2D matrices. You put those together and you get the parallel BLAs using summa. And finally, you put all that together, and on top of that is built ScalaPack, which solves your systems of linear equations. And we'll talk about that in more detail next time. So that's a good time to stop. Are there any questions? Yes?
Yeah, so in these theoretical lower bounds on communication, what is the assumed model of available hardware realized arithmetic?
Of arithmetic or of communication?
Arithmetic.
So we're just assuming we're counting floating point operations, and we're doing, you know, n cubed, 2n cubed, and then, you know, so we divide that by p, and it's 2n cubed over p. We're not worried about whether it's 64-bit floating point or 32-bit floating point. It's whatever you've built in. We're just counting those as basic operations. You could be integer arithmetic if you wanted, whatever you like. Was that your question?
No, not really. So do we? So just addition, like
I'm counting adds and multiplies.
Okay.
Yeah, that's all I'm counting. You know, independent of, you know, what precision they're done at.
On just scalar numbers in the register.
Yes, exactly. That's what I'm counting. Right. So if I wanted, I could build a performance model where I took into account not just the network, you know, interprocessor communication, which is what I'm doing here. I could also, you know, worry about the fact that on each node I have layers of cache and registers and all of that, and I could say, how do I optimize that? And the answer is that locally you do all the optimizations from homework 1 on your local processor, and you do all this stuff to optimize the communication between processors. So that's why we have this picture. The local optimizations are done here, and the parallel optimizations are done there. Right, it's a stack of stuff. Yes?
In summa, when we do block by block matrix multiplication at each processor, do we use special type algorithms for that, like N2.3 or N2.7, N2.8?
Locally you're going to call just the homework 1 style algorithm. Well, here maybe you're asking this. Suppose I have a machine with a bunch of nodes, but each node is also a parallel machine. It may be a multi-core machine. And then what would I do locally there? So you can use all of these in a sort of a hierarchy. You have to ask yourself, I've gotten some local, you know, submatrices on my local processor. What's the best thing to do? And that depends. And so if it's a GPU, you're going to do something different than if it's a multi-core, than if it's a sequential processor. And so if, you know, heterogeneity is the future, you know, or the present. And so yeah, you have to use different optimizations at each layer. And the good news is that a lot of the vendors, you know, put in, you know, hire teams of programmers so that you can call matrix multiply and let them do it. And but for a lot of the other codes, they sort of just depend on us to take our code and then tweak a few parameters and hope for the best. So there's still lots of tuning that could be done. Okay. See you on Thursday.